Hi everyone! In this video we are going to go over the halogenation of alkanes. So we're going to add a halogen to a molecule that has all single bonds. Now so far we've learned how to do this with alkenes and alkynes, but here we're going to use radical chemistry to add a halogen to an alkane. So let's start with this starting material. So we have a 6-membered ring with a methyl group attached. And I'm going to draw a few hydrogens on here. And what we're going to try to determine is which hydrogen will be abstracted, or rather, which abstraction is going to result in the most stable radical. So we're going to identify the hydrogen that, if abstracted, results in the most stable radical. So in a way, this is very similar to other problems we've done. For instance, in elimination problems, we often want to determine, okay, if we remove one of these hydrogens, which one gives us the most stable carbocation? But here we're trying to figure out if we remove one of these hydrogens through abstraction, which is our radical method, then which one will give us the most stable radical. And remember that the stability of radicals is very similar to carbocations. So if you have resonance, that's going to be the most stable option. But then the next most stable option is a tertiary radical, then a secondary radical, then a primary, and then a methyl radical. So what I would like you to do is figure out, okay, if I remove one of these hydrogens, what does the radical look like? And is it stable? So go through your different options, and you can try this on your own first, and then once you're done, you can unpause the video and we will go over it together. All right, so I'm going to actually label each of these hydrogens because some of them are the same. So for instance, the hydrogens at the top, I'll highlight in yellow, and those are exactly the same as the hydrogens at the bottom here. So it doesn't really matter which one of those I take, we'll get the same type of radical. And then the hydrogen that's bonded to the ring there, now that is kind of on its own. There aren't any other hydrogens that are like it. And then I'll highlight the methyl hydrogens up above. Okay, so let's see what happens if we remove a yellow hydrogen. So we'll highlight that. And then we'll see what happens if we remove the blue hydrogen, or rather abstract, since that's our fancy radical term. And then we'll see what happens if we remove a purple hydrogen. Okay, so if we remove one of the yellow hydrogens, let's just say we're removing this one here, we call that abstraction. So Probably something would take that hydrogen, like a chlorine radical or a bromine radical. Um, so, we're kind of showing this differently here, but we would end up with a single electron left on the carbon that the hydrogen was bonded to. Now, we could have also taken one of the top yellow hydrogens, and that would have, oops, sorry, that's supposed to be a fishhook arrow, not a double arrow. And that would have given us the same exact product, just rotated, or I guess flipped. So those are the same. So I'll actually just erase one of these. Now, what type of radical do we have there? Is it a primary, secondary, tertiary radical? So the way that I figure this out is I look at the carbon that the electron is on, and I count how many other carbons it is bonded to. So this carbon in particular is bonded to 2 other carbons. So this is a secondary carbon, which means that we have a secondary radical. Now, what if we remove the blue hydrogen? Or rather, abstract. We'll use our fancy term there. Okay, so that would leave an electron on the carbon that the blue hydrogen was bonded to. Now, what type of radical is that? A tertiary radical, because the carbon is bonded to 3 other carbons. And here I'll highlight those for you. So that carbon is bonded to 3 other carbons. So that's a tertiary radical. Okay, and what if we lose a purple hydrogen? So that should leave a single electron on the carbon on the end of the methyl group. So what type of radical does that give us? A tertiary, secondary, or primary radical? Primary. Okay, so looking at all of our options, which radical is the most stable? The second one, so the tertiary radical. So if we perform a reaction with this starting material, that starting material will preferentially lose the blue hydrogen because that produces the most stable radical. Okay, so let's see how the mechanism for a reaction like this would work. So let's look at our radical mechanism. Oops. Now there are 3 steps to this mechanism. There's initiation, where we create radicals. There is propagation, and in propagation, the location of the unpaired electron moves around. So it's going to form our product that we want. And then the last step is on the next slide, termination. And this is where we're going to annihilate our radicals by coupling them together. So they're going to create bonds again. So let's go back to initiation. So this is super simple. Let's say we have bromine, and we're going to create 2 bromine radicals. So we do this through homolytic cleavage. So the covalent bond between the bromine atoms is going to split, and one electron goes to one bromine atom, the other goes to the other bromine atom. So again, this is homolytic cleavage. All right, now in order to actually initiate this reaction, we have to add energy in the form of heat or light. So remember, energy is equal to h nu, where h is Planck's constant and nu is frequency. And usually we shine a mercury lamp onto our reaction medium in order to get it to work. So the light is coming from a mercury lamp. So really you just need UV light. All right, and then once we have our bromine radicals, we can go on to the next step. So let's use our starting material from the last problem we did. So we've got our six-membered ring with a methyl group. And remember, we're going to lose the hydrogen on the tertiary carbon. And we're going to react this with one of our bromine radicals. And the first step here is hydrogen abstraction. Okay, so this single electron is going to pair up with one of the electrons from our covalent bond to hydrogen. And then the other electron in that covalent bond is going on to that tertiary carbon. All right, so we've created a whole new radical here, a carbon radical. Now, in the next step, we're going to perform halogen abstraction. Oh, sorry, I forgot our other product, which is HBr. So the hydrogen and the bromine have combined to form a single bond. Now, again, in the next step, we're going to perform halogen abstraction. So we can add more bromine, Br2, and the radical on our tertiary carbon, let's see, so that's going to come down, form a new bond with bromine, and then the other electron in the covalent bond is going to the other bromine. So we're left with an alkyl halide. So really we've halogenated an alkane. So our original starting material had only single bonds, so it was an alkane. And through this radical chemistry, we've added a halogen to it. Now you'll notice our other product is a bromine radical, which is what we started with. So this gets regenerated. Now that's great because we could then do more reactions with that bromine radical, but that's not always great. For instance, in our atmosphere, there are radicals that shouldn't be there, and through pollution and smog, and those radicals can deteriorate or break apart other useful molecules in the atmosphere, like ozone. So it's not always a good thing that we regenerate these radicals. Now, the last step in our radical mechanism is, again, termination. So in termination, what we're going to do is get rid of our radicals by coupling them. Okay, so there are three different options for termination. One, two bromine radicals can rejoin each other and form a bond. So this is called coupling. And we get one of our starting materials back, which is bromine. 2, we could show our alkyl halide product. And 3, we could potentially have our 2 carbon radicals join up. Now that, of course, gives us an unwanted product. So if I ask you to draw a radical mechanism, you only have to include one of these termination options. You don't have to include all 3. The first one is kind of the easiest, in my opinion, to draw, so feel free to use that one. All right, now you do need to be careful with how much bromine you add to this reaction. If you add too much bromine, you might see more radical mechanisms going on and other products occurring. So you do want to be careful with that. Essentially, you could end up with a chain reaction where you add more bromines than you intend to. So let's actually look at an example of that. But we're going to use chlorine for this example. And your book also goes through this example as well. So let's say that you start with methane, which is natural gas, and you add chlorine to it. Now, initially, we would assume that we're just going to add 1 chlorine to this, right? Let's see, so CH3Cl. Now, this is actually called methyl chloride. However, if you add too much chlorine, then you're going to see methyl chloride react with another chlorine molecule to produce CH2Cl2. And this is called methylene chloride, or dichloromethane, which is something we've used in lab as a solvent. Now you do want to be careful with methylene chloride because it is carcinogenic, but you just want to make sure you're wearing gloves and all that. Okay, now again, what if we added way too much chlorine? Well, now methylene chloride could react. Oops. Let me redraw my arrow in the right color. Otherwise, I'm going to get confused. Okay. So now, methylene chloride could react with chlorine to produce CHCl3, which is called chloroform. So that's what you see in movies and TV shows. Criminals, will use chloroform to make someone pass out. And then finally, again, if we add too much chlorine, chloroform can react with chlorine to produce carbon tetrachloride. Too many carbons, I'm getting confused. Carbon tetrachloride, there we go. So typically, chemists will control the amount of chlorine in their reaction to make sure that we end up with the first product, methyl chloride. So they'll have an excess amount of natural gas and just a really small amount of chlorine, and that makes sure that we don't end up with our other products. So you can assume if I write, CH4 plus Cl2, that you're just going to end up with methyl chloride. But if I add more and more chlorine, then we could end up with these other products. So just be careful with how much chlorine or bromine you add to your reaction. Okay, now let's talk about the regiochemistry of this reaction. So where does chlorine add, where does bromine add to a reactant? So let's say we have the following alkane. It's pretty simple. And let's add chlorine, and we'll use light to initiate the reaction. Experimentally, we would end up with two products. We would end up with one product where chlorine adds to the tertiary carbon, and one product where it adds to a primary carbon. Now, we usually end up with about 72% of the more stable radical. So we add chlorine to the tertiary carbon, and then we end up with about 28% of the primary radical. So chlorine will add to the end of the molecule. Okay, so what would happen if we used bromine? Would we see the same thing? What's interesting is we don't see the same thing. So we do get similar products, but, well, actually we don't. Bromine actually only adds to the tertiary carbon. So that's about 100% of our product. And then about 0% is our other product, where we form a primary radical. So you might end up with a little bit of that one, but it's not significant to any extent. Okay, so why does bromine form the more stable radical only? Why does chlorine form two radicals and two products? Well, it has to do with their stability. So if we look at an energy diagram, bromine is more stable than chlorine. So let me just write the bromine radical is more stable than the chlorine radical. And let's put fluorine in there just for fun. Fluorine's way up here. It is not very stable. Now, if they all perform this reaction, let's just say this is our energy diagram down to our product. You can see that fluorine has a very small activation energy. So fluorine actually is not going to work well for this reaction. It's going to react way too violently. Chlorine has a bit of an activation energy to get to the products. Bromine's activation energy is quite high because of its stability. Oh, and let me just label my axes here. Okay, so the red line is referring to our bromine radical. The blue line is referring to the chlorine radical. And what this kind of shows is that bromine is picky about where it bonds. Whereas chlorine is not so picky about where it bonds. So chlorine will kind of bond to any radical, but bromine is a little more choosy. It's more stable to start, so, it would prefer to form the more stable product. Now, bromine is more stable due to its size. All right, so really all you have to remember is that bromine is typically going to form the more stable product or radical intermediate, and chlorine will kind of bond to any intermediate. So whether it's a primary radical or a secondary one or a tertiary one. Now your textbook walks through this in a little more detail, so if you are more curious about the energetics or the thermodynamics behind this idea, feel free to read through that section. But I just kind of wanted you to know that chlorine's less picky than bromine. Okay, so let's also talk about stereochemistry. All right, so let's say that we have a stereocenter, or the potential for a stereocenter in our molecule that we're starting with, and then we're going to add bromine and light. What will our products look like? So where will we lose a hydrogen in our starting material? Well, let's label all of the carbons, because remember, we're trying to produce the most stable radical, which is a tertiary radical, unless you have resonance, but we don't have resonance here because we don't have any double bonds. Okay, so let's start on the right-hand side. The carbon that I just labeled red, is that primary, secondary, tertiary? Primary. Okay, so that must go, or that must be the case for all of the carbons at the end of the molecule. Okay, what about the carbon I just labeled in blue? Is that primary, secondary, or tertiary? Secondary. Are there any other secondary carbons? Yes. This second to last one and this one in the middle. Those are also secondary carbons. And last but not least, this carbon. Is that primary, secondary, or tertiary? Tertiary. Okay. So that is where we are going to lose a hydrogen, because that will give us the most stable radical. Okay, so let's write down the steps here for our radical mechanism. So we're going to start with initiation. And what will the initiation step look like? So remember, the initiation step involves the halogens, or the halogen atoms, becoming radicals. So Br2's covalent bond is going to homolytically cleave and give us our radicals. So now step 2 is propagation. Okay, so we just determined that the green hydrogen will be abstracted through hydrogen abstraction. All right, so the covalent bond between hydrogen and the tertiary carbon is going to split apart or homolytically cleave, and we're going to form a new bond between hydrogen and bromine. And then we're also going to form a carbon radical. and that is a tertiary radical. Okay, and then in the next step, we are going to perform, remember, halogen abstraction. So we're going to add bromine, and the, oh, this is going to be hard to draw, but the single electron there is going to form a bond with one of the bromine atoms, and then an electron is left on the other bromine. Now, when that occurs, actually, let me redraw the product here. Oops, not scribble on it, erase it. All right, so when that occurs, the bromine can either add from the front or the back. So this is kind of like our SN2 reaction, where something can either add from the top or the bottom. So let's just make a note. Can add from either side. So we could end up with, let's see, bromine in a wedge, and then our ethyl group in a dash. Or we could end up with bromine in a dash and the ethyl group in a wedge. And of course we also have our regenerated bromine radical. So what is the relationship between these two products that we drew? Are they identical? Are they constitutional isomers, enantiomers, or diastereomers? So there's only one stereocenter here. So they can't be diastereomers because diastereomers have two or more stereocenters. These two are not identical because if we assign R and S, we would find that the product on the left is, let's see, S, and the product on the right is, oh geez, let's see. Oh, the methyl group's in the back. If we rotate it, it's R. Okay. So these are enantiomers. So let's actually redraw these products up above just so we can see them a bit more clearly. Okay, so these are enantiomers, and we will see a racemic mixture, so there will be a 50-50 mixture of these two enantiomers. Oh, and don't forget to also write your termination step for the mechanism. So we can just draw the coupling of our bromine radicals. And I'll just put some fishhook arrows in there. Okay. So again, with stereochemistry, there is the potential to form stereoisomers during radical reactions. So you could end up with a racemic mixture of enantiomers. All right, so I think we'll stop there. But again, we just went over the halogenation of alkanes. So this is one way that you could very easily just add a halogen into your singly bonded molecule. All right, now let me know if you have any questions because radical chemistry can be a little different, a little weird, but I do sometimes like to think of it almost like a carbocation, but you know, the arrow pushing is a little different. So, all right, I will see you in the next video.